All right, so for this week's lab, we are actually um, going to be doing the reduction of camphor to isoborneol. So this is camphor right here, and what we're going to be using is sodium borohydride here, and in our methanol solution, we're going to be applying a little bit of heat, just gentle heating, just for a couple minutes, and the product after a quick workup is going to be isoborneol. So this is isoborneol. Now notice the other isomer to its right is got the OH kind of on the in the down position. This is actually called borneol. Okay. Now in normal non-pandemic times, what we would do in our lab the first week is actually take borneol and then we would oxidize it to get our camphor product. Okay. And then we would take camphor and then we would reduce it to isoborneol. And so the reason why this is an interesting process is because notice the location of the OH. It's in the down position. And then over in the isoborneol product, we have it in the up position. So there is actually a name for this. And I'll go ahead and label the OH in red for the isoborneol. And then for the borneol, we'll go ahead and label that in blue. Okay. And this borneol with the OH down is called the endo product. Okay, and then with the OH in the upper position, it's called the exo product. Okay, and this just has to do with the orientation of that particular R group, in this case, the OH. If we have a bridged compound, so this is a bicyclic compound, and this right here is a bridge, and then this right here is a bridge, and then technically this right here is a bridge as well. But if we're focusing on just this red highlighted bridge, that longest bridge is closer to the hydrogen, and so that's what classifies it as an exo isomer. Since this longest bridge on this one is closer in proximity to the OH, then that's what makes it the endo product. And so that's just a little nomenclature introduction to these bicyclic compounds, but you don't need a ton of detail. We'll actually learn more about this when we talk about Diels-Alder reactions in lecture. But just wanted to kind of give you that introduction or point that out now that we're discussing the difference between isoborneol and borneol. That is also another way we can distinguish between the two, calling them exo or endo products. Okay, and so that is also the reason why we do this synthesis process in normal times. So we take borneol, the endo, and we oxidize it to get camphor, and then we take camphor and then we reduce it with sodium borohydride, and what we end up getting is the majority isoborneol, major product. Okay. Now, why would this be? Because if it, to me, it looks like this guy right here is kind of in closer proximity to the methyls, right? And so there's a little bit of steric hindrance there. That's true, but if we take a look at the mechanism, which we don't need to go into too much detail, but let's just look at this because we've seen this reduction of an alcohol before, or of a ketone before. But remember, this is a sodium borohydride, right? So this big guy right here is going to kind of approach from the top or the bottom. Let me highlight him. So he can come along. Oh no, that's a bummer. Let me do this again. There we go. So he can kind of come along from the top and then have that hydrogen or hydride attack the carbonyl carbon, right? This guy right here, or we can have this guy come along from the bottom and attack the the carbonyl carbon from the bottom. So attacking from the bottom would give us the major exo product, the isoborneal, and then attacking from the top would give us the minor endo product, just the borneal. Okay, so think about it when we're the reason why I'm highlighting this BH4 is so that I could kind of show you really where the steric hindrance comes into play, because we've got this methyl group right here. If this guy comes from the top, then it's going to be interacting, kind of bumping heads with the methyl group, and so it actually is easier for this this BH4 to kind of come from the bottom and approach from the bottom, and that's why we end up getting the major product being the exo product, where the sodium borohydride approaches from the bottom, the least sterically hindered approach. Okay, so let me go ahead and make a note of that. So that's less steric hindrance on the approach of BH4. Okay. And there you have it. So now that is the synthesis, right? Now what we want to talk about is the next step in this process, which would be the workup. So the workup, after this reaction has taken place, what we want to do is kind of isolate our material and purify it, right? And so this is going to be in solution with methanol, right? And so what we're going to do is we're going to add water to form a precipitate, because again, remember the number of carbons in this particular compound, isoborneol, is much more than 5, because remember the ratio of polar functional groups has to be 5 or less for every polar functional group that can hydrogen bond, and so we only have that one OH group, and so that means that this material isoborneol is not going to be water soluble, and that's why it precipitates out. So once it precipitates, we will filter it, and then we will add methylene chloride and then dry with sodium sulfate. I thought I was going to run out of space. Na2SO4. All right, so sodium sulfate. And then after that, we will filter again. And then we will boil off the methylene chloride. So we've done this, or we've seen this done quite a few times now, so this process should not be new to us. After we've boiled off our methylene chloride, we have isolated our product. Okay? And then we get to analyze it. Okay? So that workup is to purify and isolate our desired product, and then we get to run the analysis. I do want to point out that there is no further purification. Okay, and so what I mean by that is we're not running a column, we're not crystallizing the material, we're pretty much just separating it from the reaction mixture, and then we're using it as is. Okay. The analysis of the product will consist of a melting point, it will be an IR as well as an NMR. And so in the end, when you have to write your discussion, you want to make sure that you're analyzing your melting point, you're analyzing your IR and labeling your IR spectra, and then you have your NMR, and you want to make sure that you can label that NMR as well. On second thought, take a look at this and then discuss the NMR and the fact and the peaks that you do see. And so you're going to compare to literature values for camphor as well as isoborneol. Okay, and see what you see based off of what we kind of have. And then for the, I forgot to say, calculate your percent yield. Okay. But that's pretty much it for the analysis. Okay, so let me just kind of reiterate for what we really want in your analysis. So discuss your melting point. So the range, if there's any depression, and then why or why not. Like, what are you observing? Your IR. So I want you to label the spectra that you get from me or us. So from Nancy or me. And then, so label the spectra and then compare to literature values. Okay. The NMR, same Z's. Actually, sorry, not this, not the label part. I'll put label here and then I'll cross that out. Don't do that, but I want you to compare to literature and then kind of discuss it. So like, do you see at least what you should see for isoborneol? And then your percent yield, it should be pretty easy. But of course, also your sources of error, right? So I'm not really going to tell you everything you need to write in the lab report, because you should just follow the guidelines and the syllabus for that. But your sources of error, or my sources of error, I do a couple intentional things just to kind of give you something to talk about. But then that's up to you to kind of pinpoint them and then discuss them. But again, I'm not going to go over every little thing that you need to discuss. The list of things here are more or less specific to this particular lab, but then just double check your guidelines to make sure that you've covered all necessary material. Okay, and again, just in case you don't catch it in the video, the melting point, the lit value for the melting point is 212 for the racemic isoborneol. So going back up to this isoborneol, this is one of two enantiomers that can form or that are in existence. So you can also have this guy right here, where the methyl is actually on the other side, and then the OH is also on that same side. So they are non-superimposable mirror images, so they're enantiomers. But don't worry about that aspect of it. Just know that when I mention racemic, it's because there's two enantiomers of that isoborneol. Okay, I think that should be sufficient. It's a good start for the semester, right? We don't want to get too crazy. So have fun with the video and the information. We are familiar with these oxidation and reduction processes, so we're not getting too big on the details for this particular experiment, but let us know if you have any questions. All right. What's up? All right, so what I got here is the camphor that we're going to be analyzing or kind of reacting. You can see inside it looks kind of chunky, almost like wet, right? So it is kind of sticky. And so that did kind of give me some trouble when I was trying to get some sample in this NMR, or not an NMR tube, I'm sorry, the melting point tube. But I got it in there. And really what I want to do first is take a melting point of this so-called camphor, as well as an IR, okay? And so I have already taken the IR, kind of set that up for you guys already. Well, I'm doing this backwards. So I'll go ahead and give you this IR before, or to kind of take a look at. The point of this is to kind of see if the sample is clean or if it's even camphor. And you can see from that IR that it does have a strong carbonyl group. And then camphor, it does really have a distinct smell, so I know it's camphor, but I just want to let you guys know it's good practice to always analyze your starting materials, because yeah, it's camphor. I'm about to get a melting point. I haven't done that yet. But in a laboratory, if you're going to take if you're really going to take some material and then synthesize something, you want to make sure it's really clean. So that way you don't, if you don't have any, if you have impurities in there, then those impurities can react further and kind of take away from your yield. They can also prove to, or kind of make other impurities that you'll have to remove during the purification process. And sometimes that can be kind of annoying. And so if you have pure starting material, that's the best way to go, because then you're minimizing the formation of byproducts, okay? And that's just gonna be easier in the end for you. It's just really good practice. Always analyze your starting materials, make sure they're clean. And then also what you can do is, now we know exactly where this sample on this instrument, or what it looks like, right? So if we take an IR of our isoborneol in the end and it looks like there's a little bit of something in there that looks like that, then we know that that's the starting material camphor, and the reaction didn't go to completion, or we didn't purify it well enough, yada, 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 right? So I think you get the point. I'm gonna go ahead and do the melting point. You know how to do that already, so I'm just gonna tell you the number, but I am gonna get that for you, okay? Bye. All right, so you can see that I actually decided to start it at 150. You can see it's kind of like, I don't know, it looks like kind of melted already, but it's not completely. I'll keep an eye on it and I'll show you in a little bit. I don't know what that blinking, oh, that blinking is not really happening. At least on my end, that's 165. Subtle changes. Should be going away soon. We'll see. It does smell good. I don't know if you guys like the smell of camphor, but a little mixed vapor rub. Boom. 167. And boom. Let's go. Okay, so I tried to do a time lapse with my phone on this, and it went way too fast. So I tried to slow it down a little bit, and that's what you get. 177-ish was the melting point though, right? So that's all. That's good enough. Anyway, this video is it's done a little bit differently than last semester. Kind of doing a voiceover, so it's taking more time, but I thought it might be useful. So right now I'm setting up a water bath. And I'm going to start some of the equipment together. So we're going to use a flask as well as like a glass stirring rod. But now, first things first, anytime you're heating a reaction, you want to get that water bath started, because it does take quite a while to heat it up. Okay, so that's what I'm doing first. And I'm also setting up my ring stand so that I can clamp the flask on top, and what I'm doing is making sure that it can go inside. Make sure it fits and everything's lined up and we're good to go before we move forward. All right, so sorry, a little angle change here. Notice I do have the hood just at that arrow, which is 18 inches. We don't want it above that. We want to make sure we're working in a safe environment. So Camphor does kind of irritate the lungs if you put too much in there. So throw some into the flask. I threw about 112 milligrams into the flask. And then we're throwing 1 milliliter of methanol using a micropipetter. It's not super important because it's just a solvent and it doesn't need to be perfect, but just showing you exactly what we're doing. We stir that bad boy up, make sure it's dissolved, and then what we've got is sodium borohydride. Okay, so sodium borohydride is a reducing agent, and we are adding again 100 and this one in this case was 114 milligrams, and we'll mix that together. What you'll notice is vigorous bubbling, and let's take a look, see real quick. Sorry it's out of frame, but there you go. You see those bubbles? There you go. So that bubble, those bubbles are a gas of some sort, right? Kind of, I'll leave that up to you to decide what it is. I will say that this happening is not ideal for me, because it just kind of tells me that if the reaction was moving forward as expected, that wouldn't happen so vigorously. So I'm a little not too optimistic on the outcome. I know we'll get product, but yeah, just to let you know, the reaction probably won't go to completion. All right, so now that everything is dissolved or kind of settled down, I guess, we don't want to put it in there while it's bubbling, because it was probably an exothermic process, and you don't want to heat something up while it's heating up on its own. So we don't want it to get out of control. So now what we're doing is gently boiling the methanol solution. So remember, your solvent is methanol, and so when you want to reflux something or heat something to its boiling point, you basically will look at that solvent, and it's about 64. All right, I don't know, I just made that number up, probably because I saw this 4 minutes later, but it is in fact 4 minutes later, and it is done heating. We really only needed to heat it for about 2 minutes, but I wanted to make sure that I got to a decent temperature and the right temperature. And you can see now that in the flask we still have some white solid material, right? That's okay, whatever, moving on, right? And so what we're gonna do now is actually add some cold water. So in this tube I had this about 3 mils of water sitting in a test tube in a freezer. So that's cold water. And you noticed as I added that, white precipitate formed, right? A pretty significant amount of precipitate. So that's cool. I'm down, I like that. And this is, in theory, our desired product. Okay, so after we add that water, let me add the rest of there. Okay, now we're gonna go ahead and filter this material off, okay, using our vacuum flask as well as our Buchner funnel. And I'm adding a little bit of water just to wet the filter paper, so that way it gets sucked down and none of this material can kind of sneak underneath the filter paper and go into the flask. Okay. And typically, remember, you always want to have a clean vacuum flask just in case you mess up and you have to retrieve that material. You don't have to do any extra purification processes. So this is a clean flask, and then I'm rinsing with a tiny bit of cold water just to make sure that we get everything we want. But check out this little flask right here. There is a significant amount of material left behind. I don't really care about that right now though. So I'm going to let that vacuum for about 5 minutes. Yay, 5 minutes later. And now what we can do is isolate or kind of transfer this solid material into another container. In this case, I'm going to use a test tube just because that's what I had clean. And I try to do it with a little bit or just transferring with the spatula, but this proved to be a a bad idea. It was going to take too long, and so what I did was I got some filter paper, or not filter paper, but whey paper, and I'm just going to go ahead and transfer this filter paper and solid to that whey paper and scrape off the solid material onto the whey paper and then pour that into the test tube. Okay, so this is me being the fastest man in the world, super scraper. And again, the reason why I'm doing this is just because transferring it scoop after scoop would just take way too long. And so there you go. Now I'll go ahead and pour this as carefully as possible into whatever container I want. But I chose a test tube in this case. What we're doing next is just kind of like a purification process. We will be adding methylene chloride and drying the sample, because we added water for that workup, and it precipitated out. We filtered it for 5 minutes, but that didn't get rid of every drop of water, right? And so what we want to do is add methylene chloride to dissolve the material. So I'm adding just a little bit, just enough to dissolve it. And so in this video, I am putting that pipette back into this stock methylene chloride. You will never do this in a lab because you shouldn't, because one student contaminates it and then it ruins it for everybody. Not only am I the only one using it, but I'm also paying attention. And no offense, but it's not common practice. Basically, in our laboratory, what you would do is pour a little bit into like maybe a graduated cylinder, and then transfer that methylene chloride to the tube to dissolve your material. And what you can see is I am kind of just shaking it quite a bit, but it might be difficult to see, but there's a little bit of material on the bottom. And so what I want to do is probably add a little bit more methylene chloride. Okay. And because what we want to do, we want to make sure that all of this material is dissolved, because if I add sodium sulfate and then I filter it, that solid material that's in there, which is in theory our product, it won't be dissolved in methylene chloride, and we'll leave it behind, and that will decrease our yield. So I went ahead and got a new pipette because I didn't know if I touched that pipette to anything and would contaminate the stock solution. So again, I'm being extremely careful, and I added a little bit more methylene chloride, and everything is now dissolved, which you probably can't see. But I'm going to go ahead and add sodium sulfate. It is anhydrous sodium sulfate, and it absorbs the water inside of this solution of methylene chloride, right? So again, this water came from the workup, and we want to make sure that this sodium sulfate, again, is not super clumpy. It's kind of like free-flowing, floating around like when I shake it, or at least moving around on the bottom, like individual granules of sodium sulfate. I'm going to go ahead and add a little bit more here because it looks like there's quite a bit of water. It's hard to tell, but the solution is kind of cloudy, and sometimes that can be due to the water present with the mixture of methylene chloride. I probably added a little bit too much sodium sulfate here, but that's okay. We'll survive. And giving a little shake just to make sure that everything's kind of flowing around pretty good. You may be able to see that it was kind of snow globing, and that means we can set that aside, let it dry, and pre-weigh a beaker, 8.053 grams for the starting mass of that beaker. I do want to also point out that in the filter flask, there's a lot of solid material in there. It might be difficult to see at this angle, the lighting, etc. But you could definitely see some chunkies in there, right? So, I mean, what you gonna do? No biggie. I made a filter pipette. Remember, there's a little bit of cotton inside of here. That way I could just easily transfer that methylene chloride solution that is sitting in a solid material, right? I don't want to transfer that solid because when I transfer it, I want to boil down the methylene chloride and then weigh the solid material left behind in that pre-weighed beaker, right? And if I transfer a little bit of sodium sulfate on accident, then my mass will be off, and then my percent yield will be off. And so we don't want that. And so that's why we created this little filter pipettes. And right now, gravity is doing a great job of just filtering that methylene chloride solution. Little technique tip: what you want to do when you're transferring you transfer the top layer that doesn't have any solid material in it on a filter, and then when it comes time to get the rest of it, you save the transfer of maybe some of that solid material into that filter. You save that till the end, so that way the filter doesn't get clogged and your filtering process can go by much faster. So now that I have a little bit of material in there, I squeeze the top with the pipette bulb, and then I remove the pipette bulb and then release the pipette bulb, so that way I don't suck up that filter paper or that filter, that cotton that I've made. And so now that I have all of my methylene chloride solution with my product, the isoborneol, or at least what I think is that, I have it in my flask. Damn it, it's a beaker. And I'm gonna boil off the methylene chloride. It doesn't seem to be sitting into the water very easily, so I take that off. And when I take it off, I realize that there's actually a crack in the beaker, and so I have to pre-weigh something else. My bad. 23.737 grams for that pre-weighed Erlenmeyer flask. Here, there's that crack. I'm not sure if you can see it, but right where the light is, boom, right there. Maybe you saw it, maybe you didn't believe me. But that transfer of material, I mean, you saw there was a little glaze inside of that beaker. Maybe I left something behind, but it's all good. Transfer the liquid to that pre-weighed flask again, and then I clamp it, and I'm just gonna hold it in the water because for me personally, I like to make sure that I can regulate how quickly this methylene chloride is leaving. Here's the thing about camphor, right? You can smell it, it's very strong. That means some of that material is kind of floating up in the air, right? And that's at room temperature, so imagine heating it. So you might lose some during that boiling process. Right now I'm just showing you that there's very, 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 very little liquid in this flask, and we still don't have a solid present. Sometimes materials are very, very soluble in the, like methylene chloride, for example, and so they might not kind of appear until the methylene chloride is completely gone, or even until it cools. And so we'll heat it for a little bit longer. I don't want to overheat it again because I don't want to heat off that camphor product. I'm sorry, I said camphor. Isoborneol, which is also pretty aromatic, like smelly. You can smell it. It smells similar to camphor. So this material is still not showing up, but I wanted to show you that as you let the flask cool, so this is me kind of cooling it down with my hand, and then I'll show you the bottom of the flask. Not really much going on. Sorry about that camera angle. I forgot I got a tripod, y'all, and I forgot it. So this is my camera just sitting here, so the angle's bad, but you could still kind of see where right now I'm still cooling it, and this is so bad. But the Erlenmeyer flask is, you can start to see some solid material showing up as I cool it longer. And so what I end up doing is I'm going to go ahead and throw this inside of the freezer while I kind of clean up my lab mess. But first, I want to make sure we get this good view of the solid material. You can see it's like magic before your eyes. Boom, all that solid on the bottom, looking pretty good, right? So I'm just still gonna throw it into the freezer real quick anyway. That's the final mass. 23.772 grams. Here's another look after the freezer, just to show you the solid material at the bottom. Now let's take a melting point. All right, so you can see that it's pretty, the stuff on here is just kind of stuck to the wall. So what you want to do is just kind of scratch the walls like this, bop, 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 bop. Bada bing, bada boom, and you can see, let's see, there's a little solid in there, right? So then now what we can do is give it a little tap, tap, tap. You know what I mean? Tap, tap, tap in. Let's go into the bottom, you know, rinse and repeat, and then you're good to go, okay? All right, so it's above 200, the melting point of isoborneol, and I started at 164 just because camphor is around 175, right? So I'll go ahead and get my ramp rate of 5. My stop temp doesn't matter as long as it's above the possible melting point of our material. It says it's ready still. I'm gonna press that button to start it, and now it says melt. So we'll go ahead and keep an eye on this, see what we get. Looks like something's happening around 170, so that's not super cool. Kind of expected though with how much it bubbled after the addition of the sodium borohydride. But we'll keep an eye on it. Oh yeah, look at that. Okay, and 176. Please stay. We want it to stay. Holding strong. Look at that. Okay. 177. Do your thing. Dang, diggity, dang. All right, we'll check back in a minute. Here's another time-lapse video. Sorry, I just wanted to get you a look at the whole process. I don't know why. Just for some reason, so you believe me or something. But there you go. Oh my goodness. There she blows. Iceberg right ahead. Most of it's underwater. And that's what's around 200. Okay, that's cool. That ain't bad. Okay, so here's the thing. I think racemic isoborneol's melting point is about 212. So that was 200. Let's call it 200. So yeah, I'm thinking. Here's what I'm thinking. It's definitely started melting like way early, right? Like around camphor. So I'm thinking the IR is going to look like a little bit of both, right? So let's see. All right, just to remind you, you put 80 milligrams of KBR in there with 1 milligram of your sample, and then you grind that bad boy up. And then you place this on here, and then you fill it up just to create a nice little layer that you can smash to once you put in there and press for a minute. And then you should hopefully get at least part of it that's kind of translucent. We'll see how this goes. I'm gonna go ahead and place this in the IR machine, which I've already run a background on. That's what this is. And then I'll go ahead and click measure, and then measurement again, and then sample scan. See what this looks like. It's live. All right, so as expected, got a little action right here now. We've got a little, that's whatever, that's always gonna be there. But then you got a little some right there too. So I'll print this out, you guys can compare and explain, right? And then I'll get you an NMR as well so you can analyze that. Here's an NMR, ain't she purty? Actually, not really. So remember, this is a 60 megahertz instrument, so the resolution is kind of poor. But what I could have done is probably run more scans. So when you run an NMR, you put in the number of scans that you want to run. So let's say 12 scans, and then you get an NMR. So the more scans you run, the better the NMR will look. So this little scribblies on the bottom, the baseline, sometimes like that's kind of, it looks really scribbly, right? And so if I ran more scans, it might actually smooth out, and the rest of the peaks, for example, the one that shows up around like in between 3 and 4, that peak right there would actually become more resolved and more distinguishable from the baseline. Okay, and so that's the more scans you run. But I already ran 64 scans, and it takes a while, and it would have taken much longer to get something that would be like a really good NMR. Plus, there's still a mixture of materials in here, but this is the extent that we wanted to pursue this particular synthesis, and so that's pretty much it. But that's it in terms of analysis. We did a proton NMR, we did an IR, we did a melting point. Okay, so now time to clean up. All right, so obviously we want to maintain cleanliness in the lab, and so this guy right here, you can actually use it to get any solid material that you may have spilled. I might have spilled a little bit. You just want to be gentle when you're doing this, but that's the purpose of that. You also want to make sure that we're spraying down things and we are cleaning, leaving the lab not just clean, but ideally cleaner than when we got it. And I will say, even though we do a good job around here cleaning, hasn't been occupied for a while, and so it was a little dusty. So this is definitely going to be cleaner than when I got here. And another thing, you want to go ahead and, oh yeah. Woo. All right, I'm gonna get underneath this what is it called? Scale. Okay, so then that way I can make sure that I left this place better and cleaner than when I got here. I'm gonna move this back. Oh yeah. And there you go. I also did clean in here already. Oh my goodness, it's gorgeous. Those are kind of like burn stains or chemical stains. So yeah, still clean. There's our waste. I went ahead and put everything in our waste container that was left over from the reaction. Of course, you got to make sure that that waste container has those reagents on there before you put them in there. Okay, and I think we're good to go. Bye.